Hello everyone, my name is Matthew D'Antuono and I'm going to walk you guys through the final project that I did in this spring 2017 semester of Engineering 460. To begin, I'm going to give a little bit of a background on my scope. What I was trying to do was optimize the multiple traveling salesman problem, or the MTSP, you may have heard of it, using some kind of business function. In other words, I wanted to be able to take what I have listed here as my inputs, my number of trucks, in this case, for the sake of the DOE, we ran it 1 to 10, my number of locations, again 2 to 200, and my minimum tour, just meaning how many locations every truck has to take at minimum, of 1 to 5. And I want to create a function that can take these inputs and spit out an answer without having to go through a lengthy heuristic, such as I'll show you here in a second. So again, the overarching theme here is model optimization. We want to minimize the energy, the cost, and the time, and we want to do this through simulation of the TSP with variable trucks. So that could mean one truck or multiple trucks. We have 1 to 10, as you saw a minute ago. And this is all subject to a minimum tour, meaning that each one of the trucks has a minimum number of cities that they must visit. Here you see the process flow, which shows our inputs and our transformations and our outputs. Again, we see that the number of trucks, the minimum tour, and the number of locations is our input, and what we want to see from this output is our cost, our time, and our energy, and we want to see that minimized. And so what we're trying to do is come up with a formula, or a function, rather, that would be able to do this for us. So the goals of this are to obtain experimental results. So that's finding results that we can use to then run a DOE, using our DOE to identify significant factors, and then from here we should be able to regress on the data and formulate a business function that can tell us what our costs, our time, and our energy should be based on a given set of inputs. So here we have a little bit of code showing how I implemented the MTSP using a genetic algorithm. So what I did here was I needed to initialize the number of locations, the number of trucks, the minimum stops, and then the number of times that I wanted to run the simulation. Basically, all this code does is it enters these inputs into a function called MTSPGA, or more particularly ENGI 460 MTSPGA, and runs these inputs through that function in order to output what the minimum time, the minimum energy, and the minimum cost would be given these parameters. Running these enough times with all of our different variations of inputs will give us enough information to be able to run a DOE and figure out which factors are significant. Just to go a little bit more in depth with a genetic algorithm, I'm going to explain it a little bit. Here I have pseudocode. The code for the genetic algorithm is quite long, but the gist of it is that we want to initialize our first route. Generally, you want to initialize your number of cities, number of locations, and your minimum tour. However, like I just showed you, we do that outside of the actual function. So that's unnecessary in the actual genetic algorithm function itself. So the first thing we want to do after that is create n permutations of the initial route. So however many permutations we need, we want to create that many. And then we want to set a number of iterations. Basically, a genetic algorithm will keep running until it has reached as many iterations as we have told it to. So for 1 to that many iterations, we want to randomly reorganize a temporary population, just meaning that we don't want all of our similar permutations next to each other. Every time we come back to the top to run another iteration, we always randomly reorganize to mix up if we have a cluster of really good routes. We don't want to get rid of all the really good ones all at once. We'd rather spread them out and give them a chance of being mutated to become better. So for 1 to our population size, we take 8 at a time. We figure out which one has the shortest route, and we get rid of the other 7. We save that. If that shortest route is shorter than the previous shortest route, that'll become our new one. And from here, we take that one best of 8, when we mutate it in a bunch of different ways. We swap it, we slide it, we flip it, modify the brakes, flip and modify brakes, swap and modify, slide and modify, and then do nothing. Leave it as the original best that we had. We then take these 8 routes and add it to the temporary population. After we've come up with enough routes to create a new population, we go back up to the top, we reorganize, and we run through it again. Here you can see the design of experiments we've come up with. These are the last few runs that we have. This is 225 through 250, as you see here. And what this does for us is it shows us, based on with this number of cities as our input, and with this number of trucks as our input, and with this number of cities that each one has to go to, the Mentor, what our minimum time, our minimum cost, and our minimum energy is going to be based on the MTSP genetic algorithm code. So what we had to do in order to receive these values was run the genetic algorithm with these different values a bunch of times to see what the value would be. This should be able to tell us what factors are significant and set the baseline to be able to regress and find a function that can capture the main idea of the MTSP problem. So here you see we have our significant factors going down from most significant to least. We have our number of cities that's clearly the most significant, and our number of trucks, which is also very significant, as well as a relationship between cities and trucks. Cities minus 108 times trucks minus 5.5, which again gives us significance. However, we see that our Mentor, which was one of the factors that we thought might be significant, did not end up being significant. So for results, again, the leverage plots will show us the number of cities, extremely important. You can see how steep the slope is on the leverage plot. Trucks, important but not quite as much, and then minimum TOR, not really at all. So out of the factors we searched, we found the significant factors to be location and trucks. Unfortunately, these inputs and this data found did not provide enough insight to create a business function to accurately represent the MTSP GA. I believe that the reason that we were unable to create the business function was because of the randomness of location selection. Every time that we run the MTSP function, the genetic algorithm function in MATLAB, it randomly generates different points. And the problem with that is that even if you have the same number of inputs, the minimum time cost and energy used with those exact same inputs will change every iteration, which is simply leading to think that more significant factors are not being addressed. So in the future, it may be good to continue looking into which other factors might be significant, whether it be the randomness of location selection, or even just how the number of locations can affect the change in distance upon each iteration with the same number of factors. Thank you very much for listening. I hope you learned a little something about the MTSP and the steps taken in order to try and find a business function to handle the problem. Good luck to you in the future.